My name is Sangaya Hiremat, and today we have chosen a topic about music for this presentation. And the title of our project is Music Recommendation System using KNN. And we are six members in the team. First is Ayush, Mohammad Anjal, Mohit, and myself,
Hi.
Sangaya Hiremat, Saurav, and Shashikant. Can you go to the next slides, please? And the objective of our project is to build a music recommendation engine that suggests similar songs based on the song that he has selected and not on the user history or preferences. Mainly here we are using music features, not the user history and preferences. And the overview of this project is we have built it based on the recommendation. Again, as I said before, the input is the user will select a song and then he click on the recommendation, and based on that 5 or 10 songs will be recommended based on the characteristics of the song he selected. And we used k nearest neighbors algorithm in this project, and we have used fast API to deploy the code. I'm handing over to Ayush for the next slide. Thank you.
In our recommender, we leverage scikit-learn's nearest neighbors, class trained on a set of 14 standard audio features like think energy, danceability, tempo, valence, and the like. By scaling each feature to zero mean and unique variance, we ensure no single attribute dominates the comparison. Rather than Euclidean distance, we use cosine similarity. Essentially, the angle between two songs features a feature vector which perform better in high dimensional spaces and give a more meaningful measures of sounding alike. When you supply a song ID, the model simply looks up the track's features vector, compute the cosine distance from it to every other song in the dataset, and then picks a top n with the smallest angle, that is the highest cosine similarity. Because this is completely unsupervised, no labor or listening histories is required. So it handles the uh, whole start cases out of the box. All of this runs in the memory and returns the result under the 100 milliseconds, giving us fast, transparent, person similar recommendations. Now I would hand over to Mohit.
Thanks, Ayush. So, okay, now we know how our song finder works. So now let's see who can use it. So for educational purpose for student and music app, think of it like a first year music student. She just learned the word tempo and how fast the song is. So with our tool, one click shows 5 songs that all feel alike but have a different speeds. Because we only use sound facts like speed, energy, and mood, so it big hits and small indie tracks shows up side by side. So student hear more kind of music, and Discovery app can do the same. Start with a jazz tune, jump to a funk song with the same groove, and that way we can land on like chill lofi tracks that match the beat as well. So it's an easy path that keeps listener curious and happy. So now we turn book terms into a real sound. Learning becomes listening. So for shops and new streaming services, next slide. Stores and new music apps have a big problem, no listener history, and how do you pick the right song when you know nothing about the person? So because we judge tracks only by their sound, we can suggest a good song the second someone opens the app. We built a ready-made mood list like relax for cafes, pump up for gyms, like that comes under our future research for this project as well. And that list refreshes by itself, so staff don't waste time. Test shows shop managers spend around 25% less time fixing playlist, and new app user listen 15% longer. So bottom line is that we give you the perfect tune fast, no thumbs up or skips needed. Thank you.
Yeah, if you look into the dataset and pre-processing, for this project, we have used the Spotify dataset, which contains total 232,000 tracks in total and also have 18 key features. So the dataset includes both metadata such as track name, artist name, genre, and track ID, and also audio features like danceability, energy, tempo, and loudness. We also add a popularity score to help boost the relevance of our recommendation. Moving on to pre-processing, we first filled in the missing values in the columns like track name, mode, and etc. And then we have converted the categorical variables into the numerical variables. Like, for example, we have musical keys, which were mapped to C, then they became to 0, and then we have G that has like mapped to 7, and we also have modes which we have encoded as like minor equal to 0 and major equal to 1. And also we have extracted a numerical representation of time signature. And then finally we have applied feature scaling using the standard scaler, which measures that all the features contribute equally to the distance calculation. This also gave us the final vector of 14 normalized features, including key aspects like tempo, loudness, and popularity. Can you go to the next slide, please? So how does the recommendation work is, so firstly we input the user, like the user selects a song from list and like clicks on the recommendation button. And then what happens like behind is, first like we extract the feature vector of the selected song, then we calculate the cosine similarity between the vector and every other track in the dataset, uh, and then we sort the results and then return the top 5 most similar tracks. So in the output, like we get the result in the form of the ranked list of songs, including the track name, artist name, genre, and other similarity scores. Uh, so basically, why this works is it basically allows us to make recommendations without needing of the user preference history, and also it focuses purely on the audio profile, making it great for discovering similar sounding tracks. And it's like more fast and scalable, and also uh, good when you use of like pre-computed vector space. From here on, Anjal will continue.
Thank you, Shashikant. So let's go into a live demo. The application is currently running on my local and can be accessed through ngrok. And this is the URL that you can use, or alternatively, you can scan the QR code and access it on your phone. So going to the application, I'll just quickly refresh the page. So the application opens up to a homepage where you have a list of songs. These songs come from the dataset and through an API, a listing API. This is a paginated call, and it provides around 10 to 15 song elements at a time. Now, if you want more songs from the dataset, if your current song is not in the list, you can click on load more, and there would be more songs loaded. So these paginated calls are in memory stored. The previous calls are stored in memory, and you don't need to go to a previous call uh, to load the previous data. And how the recommendation work is you select a particular song and click on get recommendations, which again triggers a post API with the particular track ID for this song. You can view the similar songs on the next page, um, which would be the next 5 songs. We have capped it at 5 at the moment. It can be improved to the next 10 nearest neighbors, or probably 15 or 20. The back functionality goes back to the initial page, and you can do the process again. And the initial load of the songs are still in memory and can be accessed from here. As you saw, the input interface was pretty straightforward. You have two CTAs. One is the load more and the get recommendations. The load more would make the next paginated call, and get recommendations takes in a parameter of the track ID. You can activate it by the selection in the checkbox. The output recommendation would give you the list of X number of songs. Right now we are like I said, we are capping it at 5, but you can make more recommendations. Handing over to Saurav for the next. Thank you.
Thank you, Anshul. So the next steps and enhancements would be, the first one is the autoencoders. basically to reduce the feature dimensionality or to optimize the similarity search speed without losing essential audio traits. And the second one is to capture the nonlinear dependencies between the features, like example, the tempo and the energy, the interaction, because it should be mostly based on the accurate recommendations. So moving on to the hybrid approach, it is basically used to combine our content-based model with the user behavior data. Example by listening to patterns to support personalized suggestions, and even to overcome content only by limitations based on users' preferences over time, because it might change and improving long-term resilience. And talking about the cloud deployment, so deploy the fast API back into the cloud services like AWS or Azure for scalability and high availability, and to enable real-time API integration into mobile or web apps with low latency and high reliability. So talking about the A to B testing, the testing is based on different models, the KNN, auto encoder enhancement, and hybrid. On real users is used to measure the actual engagement impact. And second one is to use qualitative matrices like session time, CTR, and repeat visits to refine model effectiveness. So can you move on to the next slide, please? So, talking about the conclusion and then next steps based on the real-time work applications, the key benefit is for the content-based, as explained in the slide 2, and for our model depends solely on audio features like tempo, energy, etc. So, no user input is required to generate songs or the relevant results. And cold start friendly, and talking, unlike collaborator systems, our engine performs very well for new users. And scalability, the current implementation can uh, basically effectively handle large data sets up to 3 millions of tracks. And talking about the explainable, because the recommendations are based on observable features, it's easy to understand why two songs are matched. And moving on to why how works on real world application is a model can be applied in multiple domains, like streaming platforms. So when I'm going to talk about streaming platforms, it is for immediate song recommendations upon sign up, solving this cold start issue. And the playlist generation tools is to auto generate playlist based on song audio signature. And music similarity search is for your basically DJs and song designers could find similar tracks for remixing or mashups or any mood list or mood based playlist. And user engagement features. So when I'm going to talk about this, it's surfacing similar songs helps users stay engaged longer by keeping the listening experience more fresh. Can you move on to the next slide, please? So here are the references. We used the Spotify million song dataset as our core data source, and Skykit learns nearest neighbors for our KNN model. And the backend was built by using fast APIs and feature extraction techniques reference Spotify web APIs and process using pandas and NumPy. This is about it. Thank you.
Thank you, everyone.
Thank you all.